Good evening. Welcome. Thank you so much for coming out tonight. First of all, I would like to thank LinkedIn for so graciously hosting us. I'd like to introduce Laura, who actually has spoken at our meetup last year. She was at the workshop. How many of you made it to that workshop? Okay, yeah, it was a great workshop over at Stack Overflow. We're going to have the advanced talk on neural networks. Yeah, that's it.
Thank you. So thanks very much, Women in Machine Learning and Data Science and LinkedIn for inviting me here. I'm really very happy to be here to talk about a topic that I enjoy learning about myself so much. Just to give a little bit of background, so my name is Laura Graesser, and I am in my last semester of a master's program in computer science. And I've been specializing in deep learning, hence the topic of this talk, and it's something that I just love learning about, talking about with people, not just because it's sort of blown up and is kind of driving the state-of-the-art progress in machine learning, but also because it's a sort of they're a very elegant and flexible family of algorithms to study. So I think quite recently there's been lots of debates about what deep learning is, and it's been described as differentiable programming. And that is, to me, that's a sort of description that I really like, because it sort of captures this notion of deep learning as a sort of methodology for learning from data. So a methodology that is sort of based on a set of principles, so that of stacked layers of computation with nonlinear activations, along with a set of techniques for kind of making that work. And so to me, that really sort of captures the kind of massive breadth and potential ways in which you can design networks and the ways in which you can apply them to problems. So today's talk about convolutional neural networks. I'm going to assume that everybody knows what a neural network is and how to train one. And so really what today we'll focus on is the sort of properties of these networks and why we have them and how they differ from the kind of more straightforward multi-layered perceptron that I think most people start learning about when they start learning about neural networks. There's a code repo that goes with this. The link is to the bottom on the bottom of this slide. Because there's quite a lot of material to cover, this is not going to be a hands-on talk, although you're welcome to try things out as we go through. But really what it's intended to do is provide you with some more material to go to afterwards, if you're interested and kind of got hooked after this discussion. So what we're going to cover today is we're going to start with an overview of what a convolutional neural network is, and then we're going to sort of motivate it looking at the inspiration that it takes from biology and also the sort of problem that it's solving in machine learning. Then we're going to go sort of step by step. We'll start with walking through what a 2D and a 3D convolution is, and we'll then build up to the different components of a convolutional layer. So we'll talk about kernels, padding, stride, and dilation. We'll also briefly mention pooling layers. And once we've kind of gone through all of that, we'll just go through the code for a simple convolutional neural network in pyTorch. I am not going to go through the general workings of pyTorch. It's a really nice, very sort of flexible, easy to use library for sort of building and training neural networks. If you've used other libraries, and I think a lot of the different elements should be familiar. And so what really this is going to focus on is sort of the principles of these convolutional networks and how you build them in pyTorch. And what we're not going to talk about is all of the kind of training and evaluation code that goes around it. But what I have done is provided you with examples to kind of to work with afterwards. So then after that, we're going to look at two different kind of flavors of convolutional network. So the VGGNet that came out of the Visual Geometry Group in Oxford in 2014. And then finally, a kind of whistle-stop tour of residual networks. And this, once we get there, this will really take us up to the state of the art. And please, if you have questions or comments along the way, it's really nice if this is sort of interactive, so don't hesitate, hesitate to ask. And it's sort of much better if you ask the questions as they come to you, and then we can have a discussion right there and then about it. So briefly, it's sort of interesting to look at what convolutional networks are, and the easiest way to do that is to compare them to the multi-layered perceptron. And this will also give a bit of a recap for anyone that's feeling kind of rusty with what that is. So a multi-layered perceptron is a network that has a particular structure. So as with all neural networks, it's organized into layers that have nonlinear activations between them. But with the MLP, every node in each layer is connected to every node in the layer below. So we have what's called a dense set of connections. And what this does is it's very neutral about the type of data that you're giving it. It doesn't encode much prior information at all about the domain of data that you're using. But what it does, one of the consequences of this is that it tends to have a lot of parameters. So it gets computationally expensive very quickly as you increase the number of layers. The other thing is that we have a sort of flat, unstructured input. So we have a one-dimensional input. Our data is structured into a one-dimensional input vector. Now, in contrast, a convolutional network is a network that has convolutional layers in it. And these encode more structure about the domain of inputs that go into them, and this is typically images. And how this differs to a dense layer is that instead of this sort of full set of connections, what you have is local connections and shared weights. And specifically, this weight sharing is shared across space. So what does that mean? It means operations that happen on different parts of the image are done with weights that share the same sets of parameters. And we'll go into that in a lot more detail later. But what this does at a high level is sort of encodes a sort of set of properties that we know images have. So we know that there's a lot of local correlation between pixel values in images. We know that they have organized into a sort of two-dimensional structure with a number of planes. And we know that objects don't have to appear in exactly the same part of an image for us to be able to recognize them as the same object. So they have this sort of this translation invariance property. And so what does that mean about the type of inputs that go into a convolutional network? Well, they also have more structure. So they generally are two-dimensional for grayscale images, three-dimensional for color images, or four-dimensional for sequences of images, so when you're starting to incorporate video. And one of the consequences of this is that you've typically got many fewer parameters than for a sort of equivalent. It's hard to exactly say what equivalent is, but for an MLP, because of this sort of local connection and local weight sharing. So why would we want to do this? We already have one of a clue from the previous slide, which is that convolutional networks typically have fewer parameters than fully connected networks. And why might we want to do this? Well, in machine learning, and particularly in sort of neural networks, they can suffer from sort of over parameterization. So they have they are capable of approximating very complex functions and have many parameters. And in fact, it's not uncommon for there to be more parameters than data points. And so what can happen is that you get this poor generalization ability of the neural networks. And so given this problem, what we want to do is kind of reduce the number of parameters. And what that's doing is that's reducing the size of the hypothesis space that we're searching in. And so that is going to reduce the likelihood that we're going to overfit our training data. So given that we want to do this, the question becomes, how do we do this in a sort of smart way? Because if you just cut parameters, then the chances are that you're reducing the size of the hypothesis space, but you're reducing it in such a way that you're moving sort of further away from a good solution. So you want to do this in a smart way. And so we kind of take some inspiration from biology in order to be able to do this. So there's sort of three lessons from our visual processing system that convolutional neural networks take inspiration from. So the first is that it appears to be hierarchical. So what we have is in the sort of lower parts of our visual cortex, we have neurons that respond to kind of local to more local inputs. So inputs in their locally receptive field, and they tend to respond to quite simple shapes. And as you move sort of deeper or higher up in our visual processing system, the receptive field of the neurons tends to increase, and the complexity of the patterns that they respond to also increases. So, for example, at a sort of a point sort of quite high up in our visual processing system, you may even have a single neuron that only responds to one face, not just faces in general, but one particular face. Whereas sort of much lower down, you'll have a neuron that will fire every time it sees a sort of vertical edge in its receptive field. So we've got this sort of we've got this notion of hierarchy. We've got this notion of local connections, which are gradually integrated into global connections. And we've got this notion of simple to more complex features. And this inspired this notion of the convolutional network and this structure that encourages the network during the learning process to be able to do this. So given the motivation, now I'm just going to go through, build up step by step, what is a convolutional layer, starting from a 2D convolution, building up to the full-on layer. So starting at the beginning, convolution takes two inputs. So we've got an image, and we have what's called a kernel. So a kernel will have a specific shape. So in this example, it's 3 by 3 pixels. And the way you compute the output of this convolution is you apply it repeatedly to different patches on the image. So in the example on the slide, what we have is the kernel applied to the sort of top leftmost patch. And you can imagine it just being applied like a stamp on top of this patch. And each of the corresponding pixels and weights get multiplied together and then finally summed up. So it's like a dot product with a bit more structure. And the convolution operation itself actually refers to the kernel being applied by being slid across the whole image. So you can imagine this continuing, but to apply the convolution, it is like sliding this kernel and computing one output element at a time as we go over the image. And so a couple of things to notice with the setup that we have here is we've got an output that also looks structurally like its input. So we go from a two-dimensional input to a two-dimensional output. But we also shrink the size of the output. So as we're sliding the kernel over, we have fewer fewer output pixels than input pixels. Now, once we've gone from 2D, it's sort of an easy step to move up to 3D. And so now we have the height and the width, 6 by 6. And now we can imagine that there's sort of multiple channels in our input. And for images, this has a sort of very natural interpretation, because these are the RGB channels in a digital representation of an image. And so now the one change that we have compared to the last slide is that the kernel now has 3 dimensions, and the last dimension is equal to the number of channels that you have in the input. And the number of channels doesn't need to be constrained to 3 to correspond to images. It can be any number of channels. So we might have an input which is 6 by 6 by 8. And in this case, then the kernel will be 3 by 3 by 8. So a kernel will always span the entire depth of the channels of the image that you're applying it to. So again, you can imagine stamping that kernel on this patch over the height and width, but that now it extends through the whole depth. So it has the benefit of being able to sort of take into account all the information in all the channels in that particular part of the image. And once we've got a 3D convolution, it's very easy now to build this up into a sort of full-on convolutional layer in a neural network. So what you see here is an example of kind of 2 convolutional layers. We're going to imagine starting with an input image of 32 by 32 by 3 pixels, which is a kind of very common, it happens to be the dimensions of the CIFAR dataset, which is the dataset I used for the repo. And now what you do in a convolutional layer is you don't just specify the dimensions of the kernel, so how many pixels it should span. So up until now we've been talking about 3 by 3 kernels. But in this case, we're going to specify for the first layer, it's a 5 by 5 kernel. And because there's 3 channels, it's going to be 5 by 5 by 3. And you don't typically have one kernel in a convolutional layer. You have many. And we'll talk about what the interpretation of this is in just a minute. But just working through the mechanics, now in our first layer, we've got 8 kernels of 5 by 5 pixels, sorry, 5 by 5 by 3 pixels, the channels. And then we apply that to our input image. And the output is now 28 by 28 by 8. So we get the 8 from the 8 convolutional kernels. And we get 28 by 28 because a quick way to sort of figure this out is to take 32, subtract 5, which is the dimension of the kernel, and then add 1. And that's what you'd get from sort of sliding it all the way over our input image. And so now we've got something that is of the same form as our input. And so we can do this all over again. And so for our next layer, now we've got a slightly different shape of kernel. It's 3 by 3 pixels. But because we had 8 filters or 8 kernels as the output of our previous layer, they now need to be 3 by 3 by 8 deep. And then for this layer, we're going to have four kernels. So we're going to have 4 of these. And then we do the same thing again. And now we have an output from the second layer, which is 26 by 26 by 4. So the 26 being 28 minus 3 plus 1, and the 4 corresponding to the 4 different kernels that we had in our second layer. And really, this is a very common pattern that you'll see. And basically, what we have now is a convolutional network. There's a few extra things to add, but basically sort of this is it. This idea of repeatedly applying a number of kernels to an input and then stacking that up into layers. So what actually is this doing? Well, what kernels can be considered to be analogous to feature or to sort of feature computers. And so to give an example of how that might work, is in a particular layer, you might have, say, 3 kernels, and each of them will have learned during the training process to have computed a particular different type of feature in the input image. So to sort of walk through the example here, the grid just shows where the kernel is a sort of stylized version of where each of the kernels will be applied to the image. And so if you imagine that one of those is an eye detector, what you'll see is in the set of outputs, it will be firing in, or it will be sending a sort of large positive signal in the area which corresponds to the part of the input image which contained the eyes. You can see similarly for the nose, it would fire at a different part of the image, and the paw feature detector would fire towards the bottom. And so now what you have is a set of outputs which are sending information about the presence of these features in the different parts of the image. And this also gives us a sort of clue about why the convolutional structure is so useful for images, because we don't know where the eyes might appear. And so really what you've got is the benefit of having learned a single feature detector that you're capable of applying to every part of the image, and sort of have it fire sort of independently of the position. And this is a very useful property. And then where it gets sort of really, really interesting is when you sort of study the characteristics of the types of features that these convolutional networks learn in different layers. They kind of correspond really in a sort of really intuitive way to how you might imagine building up recognizing a particular object. So this slide has sort of a lot going on, so I'll sort of walk through it quite carefully. So what you see on the left-hand side is a set of examples of nodes sort of selected at random for nodes. When I say nodes, I mean kernels, selected at random from different layers in a convolutional network. So if we look at layer 2, what you see here is the results from 4 different kernels or 4 different feature detectors. And on the left-hand side, there's a small grid of 3 by 3. And what that's showing is a sort of projection back into pixel space of what is happening when this feature detector fires really, really strongly. And this is a sort of really, really nice technique that has been developed for helping us sort of visualize what's going on. So we pick a node and we find a set of images that causes that node or that feature to fire really strongly. So corresponding to the sort of previous slide, this is an image which, as it's passed through the network in the feed forward step, causes this node to fire strongly, to say, yes, this feature is in the image. And you can see that in the lower levels, this gives us the types of features that are learned are kind of quite simple. So in the sort of the second from the left-hand side, you see the feature is sort of detecting some type of circle. And what you see on the right-hand side is just the images that caused the node or the feature to fire really strongly. And then third from the left-hand side is a feature that sort of is detecting a curve. And then if you move up, so layer 3 is sort of the next level up, so higher in the network. And what you're seeing is sort of nodes that fire at slightly more complex shapes, but it's still sort of fairly abstract. So we're beginning to get textures, and we're beginning to get sort of more complex objects. So there's a sort of quite interesting one on the right-hand side of layer 3, and this appears to be a text detector or a horizontal text detector. And then as you move up into layer 4, you're actually, I didn't make up the nose detector, you do actually get them. And so what it's doing is these nodes are making, or these feature detectors are making use of the simpler features in the layer below and combining them in order to be able to fire to recognize more complex and sort of coherent shapes. And then in the final layer, now we've moved from a sort of nose detector and we've got an entire face detector. So not quite the neuron that fires at a single face, but we're at the level of a neuron firing at faces. And so what we have now is that property we talked about at the beginning, which is local simple features that then get integrated into, or that get used and integrated into more global features. And that's exactly what we're seeing here. Yeah, so just to repeat the question. So I think that there are two parts to the question, which is sort of how complex is this model? And two, what types of objects can this model recognize? So this is taken from, the image is actually from a really nice paper called Visualizing and Understanding Convolutional Networks. And I really recommend reading it. And so I believe this network actually was trained on the ImageNet dataset. So it's the objective for that is actually to categorize an image into one of 1,000 categories. So this is just a sort of tiny subset of that like set of images. And then also what I'm showing here is not all the nodes, but just 4 in layers 2 and 3 and 2 in layers 4 and 5. And so there'll typically be hundreds instead of tens of sort of these features or feature maps, as they can be referred to in a neural network. And just it can be sort of quite common to start off with something like 32 or 64, and then typically these are doubled as at periodic points as you increase to the network. So you can end up with something like 256 or 512 as you get up into the higher levels. Does that answer your question? Yeah, it's a great question. So the question of like what nodes are actually used to recognize objects. So I think the question was like, what nodes are used, or can you tell what nodes are used to recognize objects? I think it's not entirely straightforward, and you're right, this is not exactly what this is doing. What this is doing is simply saying, find me the pictures that cause this node or this kernel to respond most strongly. And that might give us an indication about the types of feature that it has learned. But in practice, there's likely to be a whole sort of network of features that light up when you give it, say, a dog and has to put it in a category. So it'll be sort of one of many, but it does give you an indication of the types of roles that are involved. And if you go right to the top level, the top of this network will have 1,000 nodes, one of which will fire most strongly. And so you can kind of draw a tree. If you wanted, you probably could draw a tree that extended down from that single sort of node that lit up the most through the sets or the patterns of activations that fired all the way throughout the network that kind of contributed to it. So I'm going to just quickly run through a set of other things that you might come across when you need to kind of build convolutional layers. So the first is padding. And the reason we'd use padding is it can often be useful to have an output that is the same size as your input. And this comes particularly in handy with something called residual networks, where you have these sort of very deep 100+ layer networks, and you have this sort of repeated application of a sort of block of computation. And really what you want is the output to be the same size as the input. And padding is what allows us to do this. And it's sort of quite intuitive. With padding is equal to 1, you just add a pixel on each side. And so what you'll have to do is specify the padding that is relevant for your kernel size. So the way to do it is to take your kernel, which is sort of width of 3 minus 1, and divide by 2. So a kernel of 5 would have a padding of 2, etc. And for this reason, it's also kind of common practice to have kernels with an odd width and height. And just to give another sort of visual example of what's happening, so as with before, now you just imagine that your image is this size, including all the white boxes, and then you slide. So just to do that one more time, you slide the kernel across. And one quick trick to sort of figure out which pixels are contributing to which output unit. In the case that you have padding that exactly preserves the size of the input image, the pixel that the kernel centered over is the corresponding pixel in the output image. Another common one is stride. And so stride, just what that refers to is how many pixels you slide over as you're computing the convolution. So in all of the examples that we looked at before, the stride was 1. So at each step, you move 1 pixel across or 1 pixel down. But you don't have to do that. You can move 2 pixels across and 2 pixels down. And one of the consequences of this is that it sort of helps you reduce the size of the output image quite significantly. And it's sort of often used to reduce the number of parameters and the amount of computation in the network. And it sort of emerged as a more common technique for reducing the size of your network compared to pooling. I'll review pooling, which was very common, but now sort of having strides of 2 or more have sort of taken over. And you can see that you don't really lose that much detail. So it's a sort of a conceptual or more theoretical point, which is, given how much overlap there is between a kernel that moves just 1 pixel, do you need to calculate features just 1 pixel over, or can you afford to calculate them sort of 2 pixels over and 2 pixels down? You probably don't lose that much information, and you save quite a lot of space in computation. So the last one is kind of quite interesting. And is not used particularly widely, but so it's called dilation, and it refers to the amount of spacing between the pixels in the input image that is used in combination with the kernel to calculate the output. And so where this tends to be used is in tasks which involve some form of dense prediction. So say you're trying to do semantic segmentation on an image, so you actually need to output a pixel map, which is saying a certain set of things about the image, and so really what you want to do is kind of incorporate features at different scales, and dilation can help you do that, because one of the things that it does really well is it as you move up it through the network to the higher layers, if you have dilation, then the receptive field of particular feature maps increases sort of exponentially, whilst you're only getting a sort of increase, a linear increase in the number of parameters. I know I kind of went over that very quickly. I'll say how it works, and then if you are interested in reading more, then I can sort of point you towards some things. But really, now this has dilation 2. Everything we talked about before had dilation 1, and then it sort of follows a very familiar pattern. You just slide the dilated kernel over, and so the consequence is that you get a sort of much smaller output image as well. Pooling, this is mostly for completeness. I don't see this as often anymore, but pooling was a way of basically shrinking the size of your output. So there aren't any parameters to be learned in a pooling layer. It was sort of something that got applied in between convolutional layers to kind of shrink it and constrain the computation. And what it does is just take in the case of max pooling, it takes the maximum of a certain specified kind of block of pixels. So in this case, it's 2 by 2. You can also have average pooling, but you're mapping some block of pixels to a single output. And so in this case, you just slide along. In this case, it's non-overlapping because we're not computing sort of convolutions anymore. But you just divide your input image into a set of blocks and then sort of map that into a single value, in this case with the max. So to summarize with convolution, very similar to a dot product. It involves multiplications and sums. And the main difference is that it just has some structure. It's applied repeatedly, and it's applied on a subset or patch of an image. So we've got patches, and then we repeatedly apply it to different patches to get our output. For a convolutional layer consists of multiple of these kernels, and there's different sort of parameters that we can play with to get different effects and to have that convolutional layer have different properties. So we get to choose the number of kernels, which are the feature detectors, or they can often be referred to as filters. There's the kernel size, 5 by 5, 3 by 3, both very common sizes. There's the stride, so how many pixels we want to move across or down at each step. We've got the padding, so how much you want to kind of pad your image. It's quite self-explanatory, I guess. And then the dilation, so the spacing between the pixels. And then finally, you have pooling layers, which can be used to downsample the output. So at this point, we've kind of covered the basics of convolution. I'm now going to run through the implementation of a convolutional network in pyTorch very quickly. So what you see here is just actually what gets printed to the screen once you've implemented it. And the reason I include this is it's a really nice way of just sort of summarizing the structure of the network. So what this network has is a convolutional layer with 3 inputs because it's an image, so 3 input channels. We're going to have 16 filters, 5 by 5 kernel with a stride of 2. Then we're having a ReLU activation followed by another convolutional layer that takes in those 16 filters and computes 32 new features, the same kernel size and stride, another rectified linear unit, and then dropout. And then what typically happens is what you do is with the output of the final convolutional layer, you tend to flatten that into a single vector. In this case, that will have a vector that will have 800 elements in it. And then I have a final linear layer to get to the desired output. So in this case, the objective is to classify images into one of 10 classes from the very sort of classic CIFAR 10 data set. And those classes are some things like truck or airplane. So I'm going to run through this code briefly. It's provided in the repository, but the sort of main things to know about pyTorch is when you're defining a neural network, you package it into something called a module. So the way to do that is you define your own neural network class and you inherit from the module class. And this has a couple of sort of really nice properties, which is if you add your layers to it in a particular way, it's going to kind of register that and keep track of it. And so you do that here in this sort of initialization method. And then the one other thing you need to do is define the forward pass. And once you've done that, then pyTorch handles the kind of the automatic differentiation and the training in a kind of really, really neat way. So I would recommend building your models like this. The other thing that you'll see, it very much follows what we saw printed to the screen, but you'll see this sort of particular construction, which is first putting all of our layers into a list. So here I'm simply adding in our convolutional layer, and I've specified the in channels, the out channels, the kernel size, the stride, the padding, and the dilation. So all the things we talked about is sort of once the concepts are there, it becomes very easy to cover. I'm adding in the ReLU. I add in all of the layers up to the end of the convolutional part, and then I package it up into something called a sequential model. And this is sort of a structure or a container that pyTorch provides. And the really, really nice property that this has is it allows me to just call the name of the feature and put my inputs, basically use that as a function, use that as the forward function. And so when I do self.conv_model, which holds this sequential model, and give it x, which is my input, it handles the entire forward pass for you. And it makes everything so much easier. So all you need to do is just stick everything in a list, stick it in a sequential model, and then everything is sort of much more straightforward. And what you see here is something that I do really often, which is I sort of define my convolutional layers, stick that in a sequential model. I define my linear layers, stick that in another sequential model, collect my parameters together, initialize them. You don't have to do that, but if you're interested, I just defined a function to initialize my layers. And then the forward pass just becomes really, really easy. You must define this function the forward function in your class for the rest of the training process to work well. But once you've got your layers in this sequential structure, it becomes really, really straightforward. I just call self.conv_model and give it the input. It does all of the forward pass on that part. Then you need to do this flattening transformation, so which is sort of easy to do manually, and all this is saying is basically it says give me x, which will have now that it has some 3D structure. I think it's 5 by 5 by 32 at this point, and it says, okay, I want you just to turn this into a single vector, and this -1, all that does is say, okay, well, we're training in batches. So I know that this vector needs to be 800 elements long, and just structure everything else that remains as the batch size. And then once you have that, you just stick it through the flat layers, and you have your output. So I recommend doing things like this in pyTorch. Oh wait. So this kind of brings us to the end of the intro to ConvNets. The last part that I really wanted to talk about is to kind of give a flavor of the kind of state of the art models. because once you have the convolutional elements, they're really pretty flexible, and you can do some quite nice things. So what you see here is the training and test accuracy curves on CIFAR 10 for 3 models that I've sort of provided the trained versions for in the repo. The blue line is the basic convolutional network that we just went through. So it's not terrible, but it's only getting about 65% accuracy. So there's a lot of headroom. And then the other two are a VGG-like net and a residual network. And these do much better. I didn't really play around with this much at all, didn't do any hyperparameter tuning. It's all got the same settings. So I'm sure there's a lot of improvement that can be made, but I just think it sort of really illustrates the point that the residual network, which is the yellow line, is sort of, just by the nature of its structure, outperforming quite significantly the other two. And so that's I wanted to kind of introduce these types of networks, partly because they seem intimidating, but actually they're really not. And I kind of wanted to I don't know if demystify is the right word, but once there's a couple of sort of fundamental things to get, and then they become quite straightforward. So that's the sort of last part that I wanted to talk about. And you'll see as we sort of go through these two types of architectures, there'll be a running theme, and that's deeper is better. So the first network is what's known as VGGNet, and it won the ImageNet challenge in 2014. And it's interesting for a number of reasons. So the first is that it's very simple. And I've included this sort of big table on the right-hand side, which I sort of encourage you to look at after the talk. But the way to interpret it is that sort of these lines here are sort of repeated convolutional blocks. And one of the benefits of this sort of network is that it had a really simple repetitive structure. The sort of second idea that they had was to use really small kernels. So everyone up until this point, people were kind of using 11 by 11 kernels or 9 by 9 kernels, and they kind of said, okay, we're just going to use 3 by 3 kernels the whole way through. And this did a couple of things. It had a regularizing effect because 3 layers of 3 by 3 kernels actually has about almost half as many parameters as a single 7 by 7 kernel. And it also there were 3 opportunities for nonlinear activations instead of 1. And so you start to be able to both reduce the parameters and have a sort of more expressive function that you're approximating. And so the combination of these two things is they were able to successfully train the sort of deepest networks that were around at this time. And it was sort of very very effective. And so what I've done is there's an implementation of a kind of VGG-like network. So it's not exactly VGGNet, but it sort of follows the same sort of types of principles. So it's there in the repo if you kind of want to take a deeper look. But really, the state of the art now in pretty much all neural network applications incorporates a residual network in some way. So it doesn't necessarily have to be a residual convolutional network, but this sort of big idea about structuring blocks of computation in a particular way was sort of really transformative. So it was developed by a group of researchers in Microsoft Research 2 years ago now. So, well, yeah, 2 years, in 2015. And they had this sort of idea that instead of having, the main idea is allowing a skip connection. So what that means is you have a layer or a block of computation, but you also allow just the inputs to pass directly through to the next layer. And so what this does is this sort of reframes the computation of what a layer does. So you can imagine each layer is computing some function h of x. And instead of sort of asking that layer to compute this sort of function in one go, this residual block decomposes the computation into two elements. It says the computation hx is now x, so just the identity mapping, plus some function f of x. And then you apply some nonlinearity to the result. And what this really does is this allows the gradient to flow really smoothly back through the network. And it also gives the network the option of, if you've got actually learning something quite simple like the identity mapping, of just sort of passing those results on. So instead of having to kind of compute this full transformation, you're computing what's known as the sort of residual. So something just small in addition to the inputs that you have. So the consequence of this is it allows you to train like really, really deep networks. And we went from sort of VGG 19 with 19 layers to 152 layers. So because of these skip connections, it meant that you could propagate the gradients back through the network and just allow people to sort of learn in a much smoother way, and to create these sort of really deep networks. And although there isn't a huge amount of sort of theory as to why, it sort of really appears that going deeper is better. And so that's, I guess, the sort of overall lesson from these two stages of progress in sort of neural network architectures, which is both in their own way for the time were enabling training of really, really deep networks. So I'd like to end the talk by just showing you an implementation of a residual block. And really there's two parts. There's a set, like a small, you can think of it as like a small convolutional network. So in this case, we've got two convolutional layers. We've got something called batch normalization included, which is like normalizing your inputs, but in between layers. And so this sort of block of computation can be thought of as this sort of single unit. So it's taking input x and computing some function fx. And then really all you need to do to create the residual block is compute the forward pass through this small model that you've got and add in the original inputs, and then apply a nonlinearity. And so once you have this structure, and I'm not going to go through all of this in detail, but once you have this structure, it becomes very easy to build up a network of an arbitrary number of blocks. And so there's an implementation of this for you to sort of look through and to get stuck into. But then what residual networks have is this sort of very similar, very sort of simple repeating structure, which is you tend to have a layer or a layer or block of computation applied to your input image, which sort of generally reduces the dimensions somewhat. And then you just have some number of residual blocks. So it's a parameter in the network here. And you just add in this separate sort of class that we defined earlier. And then there's certain things that you can do which are up to you. So in this case, every 2 blocks, I double the number of filters and halve the size of the output. But it's sort of totally up to you. And then everything else follows exactly the same kind of structure that we've followed before, which is kind of wrapping everything up into a sequential unit and then combining that to compute the forward pass. But I think really this also kind of shows the power of pyTorch, which is it really helps you kind of modularize the different parts of your network and kind of simplify the design. So it's a really great thing to be using. So what next? Try things out yourself. Everything's in the repo, including the slides. So if you ever want to kind of refer back to them. Once you're familiar with that, I encourage you to kind of modify the implementation. So if there's different ideas that you have about applying the sort of general principles that we've talked about today in a different way, then I encourage you to do that. There's also the papers, which are really, really nice. So the kind of the paper that introduced VGGNet and residual networks, I recommend reading those. And then if you are interested in the history of where convolutional networks sort of originated, or in their links to neuroscience, then I've also sort of included 2 really interesting papers here also to read. That brings us to the end. Thank you very much. And yeah, please let me know if you have questions. So the question was, in signal processing, convolutions are a bit different. So what's the relation and why they're called convolution? So I'm not very familiar with signal processing, so sort of help me out if I get some things wrong. But there's the convolution operation, which is sort of defined as a particular, it has a particular mathematical sort of definition. This is consistent with that. And so also, so if you go back to early computer vision processing, you'll also see convolutions and kernels showing up there. So things like Gabor filters, I think, can be designed from a set of kernels. Gaussian blur filters. Also, you can, I mean, it's kernels with a particular set of values. So instead of learning the weights, you just set the weights, and then applying them repeatedly to an image will have a particular sort of outcome. So yeah, Gaussian blurring is one. Edge detection is another. Where I get less familiar is, say, sort of audio signal processing. I know less about that. One thing that is quite interesting is, are you referring to this sort of idea that the sort of relation, the way convolutions and Fourier spaces relate? So that there is also a relation here. So in some of the neural networks libraries, the convolutions actually transformed to Fourier space and then applied there and then transformed back. So as far as I know, it is the convolution operation, and there's no difference in terms of how it's sort of mathematically defined. And I think just the way it sort of gets applied or the way it gets referred to might sort of seem different. But if there's sort of anything that you want to point me towards or anything that you sort of think isn't consistent, then I'd kind of love to learn more about it. But as far as I know, it is, and is the same thing that's applied in kind of traditional image processing and other forms of signal processing.
Can you briefly explain what the CIFAR data set is?
Great question. So the question is, what is the CIFAR data set? So it's a it's a data set that's sort of really commonly used, or was very commonly used, I think, in image processing research. I think it's less commonly used now because it's sort of quite easy. But it is a collection of 60,000 color images of, they're quite low resolution, so they're 32 by 32 pixels by 3 channels. And they each contain an image of, an image which contains an object from one of 10 classes. So I know that there's things like truck and automobile and plane, and I think frog for some reason, and horse. And I forget exactly all of them. And I think it's a Canadian research group that came up with it. That's I think the C in CIFAR stands for Canada, but beyond that I forget exactly. But if you just Google sort of CIFAR 10, so if you just Google CIFAR 10 or CIFAR 100, it'll take you to a website with a lot more information about it. But fortunately, pyTorch just provides it packaged up with a library, and so you just do like pyTorch. I mean, forget exactly the code, but there's an example in the repo, but it's like one line of code, and it downloads it, unpackages it for you, and kind of turns it into nice batches of things to work with. So it's a really nice data set for sort of experimenting with, because you don't have to kind of process it or deal with anything messy. And it's sort of one level harder than MNIST, which is a digit recognition, grayscale digit recognition task. And so it's a sort of nice next one to work on. So I have actually provided some statistics on the repo about how long it takes per epoch. It takes less than 1 minute an epoch on a good GPU, but it takes about so the residual network takes about 10 to 15 minutes an epoch, and the VGGNet is something like 6 to 8 minutes an epoch. So it's not undoable. It's doable on a CPU, but you'll have to wait a few hours. And then people kind of really go to town on how many layers and things to make. Like these aren't huge. So you can, particularly with the residual network, you could get like lots and lots of layers, and then it starts to be really problematic to train on a CPU because it's just so slow. But I think all of these are feasible. Obviously much quicker. If you do have access to a GPU, it should automatically train on it. But if not, then it will also be okay if you're willing to wait a couple of hours. So so the question is, how do you come up with the number of kernels? Great question. There isn't a kind of hard and fast rule. With the exception that there is one heuristic, which is how the number of kernels tend to relate to each other in subsequent layers. So a really sort of common heuristic that people have is you start with some number, say 16 kernels, and then double it every 1 or 2 layers. With this, there's this sort of idea that you're going kind of wide as you're you start off with a few simple features, and I think the kind of intuition for this is well, there's fewer basic shapes. Exactly how many there are is sort of up to you. Are there 8? Are there 16? Are there 32? But basic sort of edges at different orientations, basic things. But then as you get higher up, so as you're say going sort of in the middle of the network, then you need to recognize sort of circles and maybe shoes and chairs and sort of complex components, and then there's hundreds of those. And then similarly, as you get higher, so there's sort of the number of complex objects explodes. So I think that motivates this going from a sort of fewer to more filters. But it's a sort of matter of practicing and experimenting. One thing to keep in mind is that it's the more filters you have, the more computation. So sometimes it's more that you're just constrained that something's going to take too long, or that you find that it's sort of unnecessary for the task. So what I typically do is sort of experiment with something between 8 and 64 starting filters, and then have some just general rule for increasing them, whether it's doubling at every layer or every 2 layers. Oh, the other thing you can do is look at other people's implementations. that really, reading other people's code about, or reading other people's papers. I mean, as a general rule, actually, and I'm not the first person to say this. So there's this great quote by Andrej Karpathy who says, "Don't be a hero." And what he means by that is people have done lots of work and are really generous about publishing and open sourcing their code and models, so use those. Start with those, like start with the hyperparameters and the structure. Find something that's sort of similar to your task and start there, provided you have the computation for it. So it's a good way. It's also a really good way to learn from other people. So the question was, is the last layer pooled, or don't you use it so much? To answer the second question first, I don't see pooling that often anymore. So having a sort of stride of 2 seems to have replaced it, but this is sort of more an observation than a sort of hard fact. I think one of the advantages of having a stride of 2 is that you don't lose resolution in the same way that you do if you take an average or you take the max of something. But you will see if you look at the VGGNet, they have some strategies about pooling, which they do periodically. So it's definitely an option. I think it's up to you. Yeah, I think that makes sense. So the question was, what do you do at the what do you do at the end, the output? So I'll just give an example here. So this is a really common or a strategy that I use all the time, which is you define a set of convolutions. So this first part of the network, the res blocks part of the network, is sort of the convolutional part, from which you'll get some output that has a 3D structure. Then I tend to always define a function which basically says, okay, given that tells me how many parameters the output has. So X will have some 3D structure, but there'll be say 1,000 parameters, and I'll get that information from this conv output size. And then in this case, what you tend to need is some final fully connected layer, because you'll have some number of parameters that say 50 or 1,000. It'll depend on the structure you determine, but then you've got your classification task or your regression task. So you need a final transformation. So this sort of pattern you see all the time, which is you have your convolutional layers, you flatten the output from that to a single vector, and then have a single linear layer to do your final transformation. One thing you need to check, and it's something that happens all the time, but say you kind of define a set of transformations, and then it sort of the dimensions don't work because your image wasn't big enough, or so there's some things you need to just keep in mind that is sort of you'll run into as you're sort of practicing, but that's mostly around, you started off by with a 32 by 32 image, and then you've got a whole set of 5 by 5 unpadded kernels, and then at some point you try and apply an operation to something that is not big enough. And so then there's probably a sign you've got too many layers, or your kernel's too big, or something like that. Great. There don't seem to be any more questions. So thanks very much for coming. And yeah, I'll be here for a bit if you've got anything else you want to ask.